have with us Dr. Dorothy Warren, and she will be talking to us regarding how to bring in more active learning or how to make your classroom more active when it comes to teaching and learning. Let me introduce Dorothy. Dr. Dorothy Warren is a freelance science education consultant based in the UK. Having started her career as a research chemist, Dorothy took up teaching in the 90s and has worked in schools in the York and northeast of England as a teacher and head of science. In 2005, Dorothy left the classroom to become a science advisor for North Yorkshire County Council, and since then continues to support many schools and science teachers across the north of England and beyond. Dorothy is currently a key member of the Royal Society of Chemistry Teacher Professional Development Team and mentors trainee teachers on the RSC Scholarship Program. Since the program started in 2013, Dorothy continues to work for and support the very successful Yusuf Hamid Inspirational Science, formerly Chemistry program in India. As a part of this work, she has visited India many times and to develop learning more from you regarding how to make our classrooms more active. So over.
Over to you, Dorothy.
Okay. Hello, everybody, and it's lovely to be with you. And thank you very much for that introduction. I actually love the song that you were playing at the start. That's a new one to me, but it's something I will definitely watch again and again, because that's what makes learning very active and interesting and inspirational for our students. So, making learning more active. That's what I'm going to talk about today, and I will hopefully talk for about 40 minutes or so and leave time for you to ask some questions at the end. Just before I start, I was watching Sir John Holman's webinar just yesterday to see what he had to say, and I was actually really pleased I did watch it, because he put in a lot of the theoretical evidence base that I am basing my seminar on today. So I was wondering how much theory to put in, and thankfully John did quite a lot of that for me. So if you've not seen his webinar, that's something that I'll be referring to some of the research he talked to, and you can always go back and listen to that. So I'm going to share my screen now, and hopefully we won't have too many interruptions. So let me just get this shared. Right, can everybody see me? Just someone give up a thumbs up to make sure we've got that working.
Yes, we're able to see you and the screen both, Dorothy. Thanks.
Thank you. Excellent. So we'll get started then. So everything that I actually do as a teacher developer for the Royal Society of Chemistry and in my other work, we try to model what we practice. So rather than giving a outline for the talk, I've actually put down some learning objectives, because that's what I would do if I was with students in the classroom or with a group of teachers. So what we're going to try and do over the next 40 minutes or so is to have a look at the supporting evidence base for good science teaching. And as I said just now, I'm going to refer back to what Sir John Holman talked about and not spend too much time on that. Ideas and strategies designed to make learning more active in the classroom. I'm going to give you some practical examples and show where you can actually access more through the Royal Society of Chemistry website. I'm going to talk a little bit about how to make remote learning interactive, because that's something that we're having to deal with on an everyday basis here in the UK at the moment, which has been a great change from where we were a few months ago, and talk about some of the latest research about that. And then finally, microscale chemistry I've got a couple of video clips that we will have a look at and think about how we can actually really use microscale chemistry to bring some of the chemistry alive. And then finally, hopefully, if I don't talk too long, there'll be some time for your questions at the end. So, improving secondary science. This is the evidence base that Sir John Holman talked about in his first series and what we are basing a lot of our work on at the moment. So I'm not going to spend very long on that. I'm just going to refer to the 7 different areas that he spoke about and then move on quite quickly. In terms of preconception, ideas that we build on input in bringing people's ideas into the classroom, we're going to look at some strategies that we can do for that, as well as using models and how we can bring models and get students to think about the different levels of models and a practical way of doing that as well. We're going to also focus very much on practical work and how we can continue to do practical work when we don't have access to a lab and where we may have to be doing that remotely. I'm very much always looking for practical ways and hints and tips that we can give teachers rather than just being theoretical. And if you've not come across it, on the education website for the Royal Society of Chemistry, we have a collection called 7 Simple Rules for Teaching. And these are articles, there's 3 articles for each rule that have been developed and written by teachers for teachers, expanding on that education reports that Sir John Holman talked about, but also giving worksheets and activities that you can use in the classroom to kind of make it much more real. So there's the URL, something to note and have a look at. A couple of the activities that I will be looking at have actually come from this series. So effective elements of effective teaching and making things more active. First of all, we need to make sure we engage our learners, and starting off with that inspirational song can only really get people engaged. So that was absolutely brilliant introduction to what I am going to be talking about. Hands-on, minds-on practical activities. Something that I am really passionate about is getting practical experience, but getting the students not only to do things, but actually think about things. Finding out what your students know at the start is really important, and we are going to have a look at a couple of ways of doing that and some resources that we have, as well as focusing on the next bit of learning. We can do that once we know where our students are. Keeping explanations clear and simple comes in with the language. We need to focus on using the knowledge, not just the knowledge, so that our students can really understand and explain things. Providing help, support and scaffolding, and finally checking understanding. So for teaching to be effective, for it to be active, the teachers are the most important people, and the interactions between the students are really, really important as well. So these are the elements that make effective teaching and make teaching more active, and that's what we're going to have a look at. So the first thing that's really important is to engage your students. There's no point just having your students sat there feeling totally bored and not having their minds on somewhere else. So they may be physically in the room but thinking about other things. So how do we go about doing that? One of the good things is using local context. Wherever you are in the world, finding something that actually will make the students hooked in to something local. Science in the news at the moment, lots and lots of opportunities for science, because with COVID-19, we are following scientists. We're looking at what is happening, developing vaccine, and that I know is bringing a lot of added interest into the classroom. Asking questions is something else that we need to encourage students to do, asking questions from the teacher, but also to each other, and using images to stimulate thinking. So if we can actually also present a real problem that needs to be solved, and I know that in the webinar that you had by Gareth Price, he talked about effective inquiry-based learning and solving real problems, which is something, again, makes things active. So I'm going to keep away from that one because I know that's something that you've already looked at. So what we really need to do is to get our students hooked into learning through engagement. So I might use some very simple activities like this. So what is the connection? I'm going to show you 5 different images. So here we have the original culture plate from Alex Fleming. We have a picture of the moon, which has some craters in. We have an apple. We have a bit of burdock stuck on some fabric. And we have a plastic bag. Now, they may at first seem very random things to actually think about. But what we can do is we can actually get our students to come up, work in groups, to think on their own, to pair, to share, and to come up with some idea what the connection is. Now, of course, if we're doing this remotely, you can use things like putting ideas into the chat. I did think about whether we should actually have some polls and things, but I thought, no, I'll just go through these different types of activities. Well, I'm sure there's lots of different connections, but the one I was thinking about is all of these actually had careful observations involved. So it shows how the scientific inquiry is really, really important. Why did we have careful observations? Well, for the first one, they're in a different order. Polythene was basically accidentally discovered through the observation of different chemists, and it happened on 2 occasions. The first occurred way back in 1898 when the German chemist was investigating something different, noticed a substance at the bottom of the test tubes he was using, and then he investigated it. And then later on, a similar thing happened again. Alex Fleming, well, he observed zones of inhibited mold growth. And Galileo, he observed craters on the moon, which basically led to all sorts of different discoveries. We have the apple, which kind of led to Newton's laws of motion. And finally, the observation of burdock, which I don't know if that's something you're familiar with, has little hooks. And when he was out with his dog, the Velcro, when he was out with his dog, hooks, these burdocks hooked into his dog's fur. And then basically that led to the discovery of Velcro. So lots of inspirational scientists, observations, stories that can really hook interest. Now, you will have lots of things in your context that you can actually use. Using the same images, we could have had something like the odd one out. Now here, it's an idea to get students talking. Somebody might say the odd one out is the apple because they can eat that one. They might say the odd one out is the burdock birds because they can stick to your clothes. The other 2 don't. There isn't a right or wrong answer, but it gets students to start thinking, putting their minds on and talking to each other and getting those interactions. Lesson hooks is something that I've been working on recently, and this is providing a context and a practical activity to get students involved and thinking as well. So here's a possible context that might work for me, it might work for you. If your students have no idea what the ocean or the seaside is like, then it probably won't. But a possible context could be, should we look good, looking good at the seaside? Should I bother to put hair gel in and do a nice hairstyle or not? I'm going to watch a very short video clip of this simple experiment with hair gel. And just think about, can you explain your observations and how would that fit into the question that I've asked and how else can we use it? So if we could have that video clip now, the one about the hair gel, that would be absolutely brilliant. Okay, so apologies about that. With this clip, we just have some hair gel. So it's something that anybody can get hold of quite easily. You can do it on a very small scale. Then we just add some normal table salt, sodium chloride. So that's the idea that's fixed with the seaside. And you can see very clearly that as that salt goes onto it, it starts to it starts to have this liquid running out of it very, very clearly. And then when you put the sugar on the other side, it doesn't. It just sort of leaves things. If you left it for several hours, then eventually that would lead to a similar type thing, but it will take a long, long way. So that's just the short clip. So if we can stop that bit now, thank you. I'll go back. I need to go back to where we were on the PowerPoint. Right. If I just share my screen again. Okay, so we saw that very, very short clip and we saw all the water coming out of it. Getting the students to actually work out what happens and explain the observations can be quite a task, but it can lead into a lot of interest if you actually have that context of where they're going on. And it can also lead to a slightly different investigation if you want to use it to start with that, looking at the difference between ionic compounds and covalent compounds, because the sugar that we saw and the sodium chloride, it's all about the charges on them as to why you get the result you do. So there is there is an activity that is on the education website that actually is all around working with hydrogels, and that is what the QR code is that we're actually showing. Okay, so moving on to think about best evidence in supporting remote learning. There's been a bit of research done by the Education Endowment Foundation, along with the EdTech Hope, which has looked into over the last few months how we can support learners remotely. And this is what they've actually come up with. And it's no surprise really that the teaching quality is much, much more important about how the lessons are delivered. So if we're not making lessons active actually in the classroom, then it will be even harder to make deliver those activities remotely. Technology is a key part, especially for disadvantaged students. We need to work out how we can work with them. But another thing that is really important is peer interactions. And they found that this provides motivations as well as improving learning outcomes and independent learning. All of these things that actually are making learning more active in the classroom also work outside the classroom. So we have different approaches to remote learning and different types of content. And it depends on what we're actually doing. But getting that interactivity, making things more active is what is really important. And I put in red there, the teaching quality is the most important. And we need to make sure that those effective elements of teaching were there that we talked about earlier. So we have two types of learning for remote learning. We have synchronous, which is learning in real time, a bit like we're doing now, where we might have a live session, we might have a live Q&A session or collaborative work where students are working together via breakout rooms or social media. We may also then, for other activities, asynchronous is not in real time. So we have pre-recorded lessons and sessions, things that people can look at later, and also thinking about collaborative work, setting open-ended questions. So whether we are working in real time together or whether we are working not real time together, this is what they have found out about remote learning. The most important things is the quality of the teaching and being able to interact with the students. Again, making and making learning more active. So going back to one of those things way up on the list that I showed you at the start, we've talked a bit about ways of engaging learners. This is a way of actually finding out what they know, true, false, or unsure. You could use this approach with your students. If you are in the classroom, show me boards is a great way to do it. If you're doing it remotely, you could actually do this using thumbs up, thumbs down, or you could use a poll, which could be anonymized or not, depending on what you actually want. And for anybody who isn't sure about show me boards, here's just a very quick image from the first time I came over to India in 2013 at the Knowledge Exchange workshop, where we were finding out about teaching and learning in India, and the show me board was introduced. So here's a question that we could have in the classroom, or we could have remotely. Very simple question. Strong answers always have a pH of 1 to 2, and then we can ask for the answer yes or no, true or false, thumbs up, thumbs down, or we could do it through a poll if we were either remote learning or not. Here is the answer, false. Depending on how dilute the acid is, it could have a pH of under 7. And this is actually really important to find out what the students know, because there is the misconception or the difficulties that students often confuse in terms of strong, weak, concentrated, and dilute. And once we know what our learners actually understand about these things, then we can move on. Another type of activity we can use to find out what they know is the use of diagnostic probes. And here is an example here. You just basically have a question, again, show me boards to give the answer in class, or you could do it as a poll if you're working remotely. And once the students have actually ticked the right answer or given back the right answer, whichever way you want, you get information about their understanding, and everybody is taking part. And this is quite an interesting one in itself, because it is something that I do quite a lot with student teachers, and often find they get the wrong answer. Keith Tabor has done a lot of work about chemical misconceptions, and you can find all of these types of activities on the education website as well. Now you have got this probe. This particular chemical stability is one question out of a series of about 10. But if you go and look at the document, it's not just giving a yes, no answer. You're then asking the students to explain why they've chosen their answer. And that goes back to that thing I was talking about earlier, not just having the knowledge, but the use of knowledge. And can they really understand what is going on? Finding out what they know, another resource that I'm using quite a lot is the Best Evidence Science Teaching, which has been put together by the University of York. I've put the URL there. And that again comes with lots of different activities, lots of diagnostic probes and concept cartoons and activities you can take and use in the classroom. It also comes with progression tables, so we can look to see, well, if they've understood that bit, what is the next thing that we need to go on? And they have resources at ages 11 to 14 and also 14 to 16. Now I'm going to move on to talk a little bit about practical work. And getting practical in India is something that is part of the IISER Pune Inspirational Science Programme. And it's something that we looked at developing, is how we could get ideas and practical work so we can access students from all different backgrounds. Now, when we actually started this back in 2013, I had no idea that actually in 2020, in the UK, we would be with exactly the same problems. So recently, I have actually learned a lot, been helping UK teachers learn a lot from this project, because what we have now got is a situation where a lot of our schools don't have school laboratories, we don't have apparatus available, we don't have chemicals around. Because of COVID-19 and schools have now reopened, students are working in year group bubbles, and sometimes they never go near a lab. So we are having to improvise and use
any space, any table, and the materials. And also, we've got to think about apparatus, because even though we may have some, it may have to come. So all of these things that you've started off in India, we're now using over here and thinking about. Here is a spirit burner that is being used to heat something that's just been made out of a jam jar. We have the bottle tops for a crucible, and the Microscale jewelers' balances to weigh things. In terms of teaching remotely in practical work in chemistry, the RSC has actually got quite a lot on the website, and here's just one of their pages under the remote teaching support that tells us about how we can do some practical work remotely, as well as some of the on-screen experiments, which actually are very good, that teachers can use with their students. Students work through them and try it before they have a practical experience. And in the time that we don't have access to labs and materials, that works very, very well. So just a couple of examples of making indicators from different flowers that people can do at home. Neutralization circles, another lovely experiment with a bit of acid, a bit of alkali. This was done with universal indicator. One of the things that we're now encouraging people to do, if they haven't got access to that, is to think about how they can do a home version with vinegar, sodium bicarbonate solution, and just on some kitchen paper or coffee filter paper or paper towel or anything that you might have. And here are the results with vinegar and sodium bicarbonate solution on both filter paper and kitchen towel, having made a red cabbage indicator. So there are different things that we can do that don't actually need to have a lab, but can really get students asking questions and investigating what type of paper makes the best, gives the best results. And here are the results after they've dried out. And you can see where the colour changes, where the acid and alkali have met in the middle. So microscale chemistry is something that actually we are using a lot more of, and it's got a lot of advantages. So I want to spend the last bit of time talking about microscale chemistry and the different advantages of it. Well, first of all, we have smaller quantities, simpler equipment, and it's cheaper. It reduces hazards, and it's something that you can really do wherever you are. You don't necessarily need to be in a lab. You can actually use a webcam quite nicely and put and do the experiment live, or you can use a visualizer. And there are lots of different advantages. The experiments are quicker, so we can spend more time talking about what we've observed and putting the models in place. We get clearer observations, and hopefully I'm going to be able to show you an example of that. And also encourages people to think about responsible use of chemicals, so we're not using so much, and it all brings in all of that environmental issue as well around disposal of chemicals. So the first microscale practical that I want to actually have a look at is a demonstration of diffusion of gases. Now you will be able to see that we are actually in this experiment using integrated instructions, which is what you can see on the screen at the moment. And I've put an EIC article link that tells you more about the integrated instructions. And these instructions are designed to really help students focus in, reduce the cognitive load, so they're not having to read lots of instructions or listen to lots of instructions as they go through. Now, we need to, going to have a look at this video clip. Is it all right for you to yeah, that would be brilliant.
Yeah, I'm sharing it. Yes.
Sure. Nirja, let me know if in case you want me to share.
Yeah, so if you could share that with us.
Share.
Okay, thank you. So with that microscale experiment, you can see very quickly the results. It's very easy to do, and we have an EIC article all about that. And these videos, short video clips, are not yet available on the education website, but hopefully they will be soon. It's something that we've been working on in the UK over the last few weeks, and hopefully they'll be coming soon. So we're also going to now look at another clip. This is a microscale experiment. There's three different experiments in this clip. The first one is around extracting a colour dye from a flower plant, how you can actually do that using everyday equipment. It then moves into the microscale reaction between citric acid and sodium hydrogen carbonate, again using everyday things that you will have at home. And then finally, it goes into an electrolysis. So it's about 4 minutes long at the most, but you've got 3 different experiments there, and have a think about, as we watch it, how we can actually use that. Okay, so if we could move on and look at the next one, please.
Dorothy, yeah, if you have the clip, can you play it?
Yeah, I can play this one.
Yeah.
I think it's I'll just wait. Right, can you I'll just get rid of the adverts. Can you see that all right? Or
No, not yet. You may have to go to the share screen option and select the
right,
video player.
Yeah, I shall do that. Just a moment. Right. Okay, can you see that now?
Yes.
Yes. Okay.
Yes, we can see it.
Excellent. And you can hear me all right as well?
Yes.
Yes.
Right. Okay. So I'm not going to have any sound on this. I'm just going to talk through it as it goes. So tulips are flowers that we have in the spring. You can use lots and lots of different flowers for this. We're just cutting up the petal with some scissors and putting it into a cup, just everyday bits and pieces, and adding some boiling water from a kettle and using that to extract the dye from it. So a nice investigation is basically to get students to look at different types of plant material, fruits, vegetables, flowers, and see what can actually come. Now it says you use a small pipette, but actually you don't necessarily need to use a small pipette for doing this that we're doing here. You can actually transfer it in lots of different ways. You can just use a small spoon, or even something like a small piece of wood to transfer it. So again, you can see the integrated instructions here, how clear it is to see what is actually happening. So they've used a spatula there to add that they've made to add a bit of citric acid, but I say you can use the end of a spill, you can use the end of a normal spoon, and then you add your sodium carbonate to it. And in the middle, we're basically putting some of the indicator that we have made. Now, there's a number of different things actually going to be going on. And one of the things about watching videos, the evidence says that if students are just watching videos, they don't do as well as when it's a teacher demonstration. But if you're in a situation where you can't actually do the experiments, or you're having to use a video to do it, a good way to do it is what I'm doing now, is to actually put the sound off and you to talk through it, and actually at different points stopping the video to ask what's going on. Well, we're not going to stop it because we don't really have that much time. But you can see now that we've pushed in the citric acid into the puddle or the drop. We've also got the sodium carbonate in there as well, and you can see the different colours. Now you can be asking the students at all different points on here, what is happening? Can we explain what is happening? We've got a solid there. First of all, it needs to dissolve. Then we've got the reaction with the indicator. And eventually, if you look very, very carefully, you will start to
observe the neutralization reaction taking place. And it is actually really good. I have done this not across over a live webcam for some student teachers last summer when we were running a session for them. We actually had it sort of set up like that. I've not done that today. So it's something that you can do remotely quite easily, but also in the classroom, it's something that students can do quite easily as well. But you can now see those bubbles and of course challenge the students to what they can actually see those bubbles and what are those bubbles. And realizing that in their simple acid, base or carbonate reaction, they see carbon dioxide coming off. Then what we're just doing here is we're just letting the electric current run through it to show the different colors, but this leads on to a technique that we can use for electrolysis, and you could just replace those carbon rods by using simple pencils with the graphite, and there is experiments that we've used there quite nicely. So you can see there, just in a very short time, we've covered sort of 3 experiments that most students should be able to access. And then depending on the level, you can go on to talk about the actual chemistry behind what is going on, the indicators, buffer solutions, and everything else. So this one was actually filmed at CLEAPS, which is our health and safety people. It's on their YouTube channel where they've got a lot of other microscale experiments as well as that one, which means that you can go and with that you can go and use that. So you can access that from anywhere in the world. Right, I'm going to go back to going to go back, stop sharing that particular bit of screen, and I'm going to go back to my PowerPoint in just a moment, just for the final few slides. Okay. Right, so microscale practical activities. So as well as actually being able to do them when you haven't got a lab, or you can do them remotely, you can show people, you can take pictures using mobile cameras. Also, there's a couple of other things about microscale, seeing more chemistry and better observations. So I'm just going to show you here. This is a traditional experiment. If you watch, you will see something happen. What we're actually doing here is we have got the lead iodide experiment. I'm also going to show it to you on a microscale level as well, and you can see the difference. So we have got potassium nitrate and we've got lead iodide, and we've pushed them into the puddle or the drop that is again just done on some laminated paper. And what you can see in the middle is your yellow precipitate. So you've got the traditional test tube experiment going alongside a microscale experiment. Now, if you think about that, what does that actually allow your students to do in terms of seeing better observations and understanding what's going on? A lot of the time, students find it really difficult to make sense of what they see in the test tube and the chemistry and what was actually going on. So seeing more chemistry, we can use Johnson's triangle conceptual development to actually try and work out and help students work out what is going on. So we've got our macro level, which is the description and the observation. Now, in the first test tube, all we saw was that yellow going really, really quickly. But in the microscale one, we can see that line that has been formed across. It's a line, and it will help students observe that actually it's not all just mixed up. Something else must have actually happened. We then have our symbolic representation, and that is actually how do we explain what's going on? Well, we've got an ionic equation, we've got lead ions, we're reacting them with iodide ions, and we made a precipitate of lead iodide, which is our yellow. And you can actually see with that symbolic representation, that is what we are trying to explain, get the students to understand. With the microscale, they can see that actually the lead ions must have dissolved into aqueous solution, and then travelled across to have that chemical reaction. And then finally, we use models, and we have the sub-microscale explanation, and we start thinking about on a particle level what is happening. And depending on the level of your students, we can talk about the actual we can talk about the actual type of particles and interactions going on. So there we have the macro, the observations, the dissolving, the colour of change. We have the submicro, that's explanation in terms of bonding and what is going on, all those different concepts out of that experiment. And then finally, we have the symbolic representation and equations there. So seeing more chemistry, I think if you're on the microscale level, it takes 2 or 3 minutes to do the experiments. You saw how quick they were on the video clips, but you can get an awful lot of observation out of it. And you can do those in different places. And there's lots more microscale experiments that you can do using more everyday bits of apparatus and chemicals. But using the laminated sheets does work well, because at the end, all you need to do is wipe the sheet and start again. So finally, just to finish with a picture of seeing active learning going on in India, checking understanding through collaborative learning, working together, having that interaction. And you can see, if you remember back to that very first slide I showed with the show me boards, where everybody was sitting in lines in rows, here we have got people working together, working with models, discussing things, and even doing an activity outside in a different environment. And when we're making learning more active, we need to think about how we are going to do it in terms of, are people sitting in rows? Are they working in groups? Are we outside? Are we inside? What sort of equipment do we actually have? And you can see here where we've got the molecular models. There's also Play-Doh and plasticine and beads and all sorts of other things that were used on that day as well. So that is where I am now going to stop. I think I've talked for long enough. I'm going back to the learning objectives that we started with, and hopefully we've pointed you in the right direction for supporting evidence, for good science teaching and making things more active. I've given you a few ideas and strategies and places where you can get these activities. We've thought a bit about remote learning and also microscale chemistry. So thank you very much for listening, and I'm sorry about the slight technical hitch in the middle, but now hopefully we've got a time for a few of your questions.
Thank you, Dorothy. It was an amazing webinar. We can see so many people saying that these microscale activities are so easy to do and will engage their students, especially in the COVID time, using the day-to-day things, as you said. It's really encouraging to see so many people saying that they will try these activities at home. So should we start with the questions?
Okay.
Yes. So the very first question is, this has come from Samarth, and he is asking, hi, Dorothy, how have you changed your interactive workshops to effective online training in this pandemic?
Right, okay, so we've changed things a lot. We are doing a lot of training through Zoom. And with our training, we are using, rather than, we're using for things like the true false type questions to talk about misconceptions. We're using anonymized polls to get feedback from the people that we're talking with. We found using thumbs up, thumbs down, some teachers didn't want to admit, I don't know, that they weren't sure on stuff. We are doing a lot of what I've just done now in terms of practical activities, showing people little microscale experiments that you can do over a webcam. The other thing that we are doing is using breakout rooms so teachers can have that time to network and discuss. So within an hour session, we try to make it very interactive. We tend to leave things only to 1 hour because we find that teachers are tired at the end of the day. One of the things we're finding, we cannot do things during the day anymore because we've had so much school closure that teachers have to be in the classroom when the schools are open. So that is what we're doing. We are adapting. It's not perfect, but it's better than doing nothing. And the feedback that we are getting is anything that is interactive in terms of teachers being able to talk to each other, share with each other through the chat is what they are wanting.
Yes, definitely. I think everyone has had to adapt, with whatever resources available. And one thing you clearly said is that teachers are overworked, and thank you for appreciating it and bringing it into your webinar as well. Apurva, do you have the next question for Dorothy?
Hi, yes, I do. The next question is from Vimala K, and it is something that all of us who have been doing some online teaching or training have grappled with, and it is how to implement collaborative work in synchronous remote learning.
It's
Dorothy?
difficult. Yes, yeah, okay, thank you for that question. That's something that we are working on. It is actually very difficult in terms of the remote learning. One of the ways that, one of the things we're trying out is having the synchronous, where the teacher is actually setting up a project activity to actually do, and getting students to give them some time to work on it, and then getting them to meet independently afterwards, where they are using their own media to talk to each other and solve the problem or work on it, and then coming back and submitting it. It's not easy. In schools where they have got a system set up, some schools are very technology thinking, they may have iPads set up, they may have a platform where students can share things. There it works well. In other places it's not working so well because they haven't got the technology in place. So not a very good answer. It's something we're working on.
Right. Thank you, Dorothy, for that. Yes, it's a struggle to incorporate some of the things that we like to do in a regular classroom in an online version, and collaborative learning and collaborative activities is one of the major challenges that we face in the online situation, I think. But yeah, one can always assign activities to a group, ask them to coordinate or through Google Classroom or Moodle or something like that, and then jointly get back to us. Yeah, so some via media, but not a very clear solution yet. Thank you, Dorothy. Neeraja, do you have the next one?
Yes. So thank you, Dorothy, for the last question. The next one is by Mausami Chatterjee, and she wants to know at what age group should we start with such active learning activities in classrooms? So,
well, we start right from go, right from primary school. Very much believe that active learning is something to engage students, make them feel happy and comfortable. And we often find that some of the younger children in primary schools are very good at active learning because they aren't inhibited, they will get on and do things. Then perhaps when they move to secondary school, they suddenly become a little more shy. There are bits of chemistry that actually, like learning the names of the symbols and the elements, that they just have to learn, and they just have to know, and certain bits of key knowledge they just have to know. So there's always that balance between some things they will have to learn, but having different ways of doing that and really seeing if they understand it. So it's that balance between, yes, there's facts they need to recall, they need to learn those. So really as young as possible, we will start doing that. Often there is a tendency when the students get older to post 16 to start moving more to a lecture style, but actually that is just as important at those things, to have promoting questions that they need to answer,
and give their own explanations. So there's all sorts of different techniques and strategies that we've not talked about today that you can use, but certainly with older students, that group work and group talking and sharing a problem. And that is, again, it's one of the difficulties with remote learning, because what we have found is as soon as teachers have gone to remote learning, they've kind of reverted back to talking at the students, and all the evidence points that it's not such a good thing to do, but people are out of their comfort zone and having to relearn things.
Definitely, definitely. And as you said, as we go on teaching more and more elder students, I guess we can increase the level of complexity of the activities and start easy with the younger kids. We can start with simple hands-on activities, but as they grow up, we can get to more inquiry-based activities and more collaborative work, as you were saying. And definitely I agree with you that we should start with active learning at a very young age as well. Apurva, do you have the next question for Dorothy?
Yes, sure. I do have another question. This is another facet of online teaching that we all have been struggling with, and that is practicals. So Mitali Bhattacharya from Hyderabad is asking, are you managing your practicals? How are you managing your practicals with students? That is the question.
With difficulty is the answer, the short answer. Practicals in online learning is really difficult. Many schools are struggling. Where we have got schools that are open, but there is still socially distancing. So where there can be small classes, we in schools, sometimes maybe half the class at once is actually doing a practical, working on their own, but then that's a lot of time. We have laboratory technicians who are having to make sure that everything is clean. There are other schools that are not doing so much practical at all at the moment. One of the things that we are trying to encourage, again, it's a bit like I modelled with the flower petal extraction, is actually to use videos, but for there to be no sound on, and the teacher to talk through what is going on, and then stopping the video, asking a question, moving on. We're also encouraging home learning in terms of simple practicals, and one of the things that we've started doing is looking at primary science, where we have in our country very simple experiments that they may do, and then looking very much similar type of experiment they can do at home, but then the questions that go around it. So you're then starting to ask much higher level questions. So simple blowing up a balloon. It may just be a kind of a change in shape at primary, but then you're asking the questions: what goes in it? Why, if you burst it, what happens if you put water in it and heat it? And you can get questions that go right the way up to kind of quite high levels about thermal properties of water and stuff like that. So where we can, finding things that people can do at home. Where we can't, using videos, but getting the teachers to not use any volume, narrate it, ask questions, and where they're in school, doing the best that we can.
All right, thank you so much. So basically trying to make do with household material or videos, but sort of augmenting it by changing the style of teaching and the style of questioning, so that even with these household and simple experiments, they get to learn more from it. That's the current best solution that one can think of right now, I suppose. Thank you, Dorothy. Neeraj, do you have the next one?
Yes, actually, a lot of questions are coming in with like particular chemistry questions. So I don't know if you would like to answer those right now, but maybe we can share those with you, so that you can maybe reply to each one of them separately.
Yes, that is fine. Yeah.
Yes, but one question that has come up is, apart from inorganic and physical chemistry, what other experiments can be shown to maybe teach an organic chemistry concept in Microscale?
Right, we have got, if there are, again, on the education, RSC Education website, we do have a Microscale section that can be used, which has quite a few different experiments on. There's a lot of inorganic anything where you've got precipitate solutions, we can do it as drop chemistry, we can do that, and even with organic chemistry, we can do that for sort of testing where you're using failing solution or Tollens reagent for looking at the different functional groups. So you can do that, anything where you're mixing two liquids or a solid and a liquid, just essentially for a precipitation or a color change, you can do around drop chemistry. There is also, I can't think of them totally off the top of my head at the moment, but on the CLEAPS website, and it's something that we can put together and share, there is things like cracking that has been done on a microscale level, using a little spirit burner to actually heat, and using a bit of glass tubing for the reaction vessel. So it's something that there is a lot of different things that have been developed, but Bob Worley, who has spent a lot of time developing microscale chemistry, who works, well, he's really retired many times, but he does still some work at CLEAPS, has got things. So those are things that I can certainly share with you, the different links to them. We have just at the moment putting together a microscale chemistry course for the RSC, which will be running at the end of November, and that video clip I showed you is part of that course. So you've had a preview. They're not live yet, but they will be at the end of the month, hopefully, and there's some more that go into that one.
Forward, looking at more exciting videos that we can share with our, especially a lot of things about the link you share. So maybe what we would do is we'll get email to everyone who is registered for the webinar series, so that you can each have a look at the various websites that she has talked about, and go through them yourselves. Apurva, do you have the next question for Dorothy?
Yes, I do. I'm actually, Dorothy, I'm going to club two questions which are sort of connected to each other, which deal with basically diversity in the types of learners that we have. The first question is by Shamala Sundari, and she asks, some students are good in practical experiments but not in writing equations, while others are good in theory but not in practicals. What kind of a strategy adapt for these students? And the second question is also sort of related to differences in learning abilities or learning preferences, and that is by Mitali Bhattacharya, who asks, what do we do, especially in online teaching, with sort of slow learners? So,
right, okay.
Your response?
Yeah, so quite a lot of questions there. Certainly, what we need to do for those who find practical work good and interesting, but the written and the theory more difficult, we need to kind of break it down into different chunks. And that's where, if you remember, I showed you the Johnson's triangle. That is something that works quite well, because you can look at the observations, then you can say, we've got these observations, we've seen what's happened, we've carried it out beautifully. Now we need to start looking at all the different things that can happen. So the idea behind that Johnson's triangle is that we start very slowly building up the different ideas and looking at maybe a card sort activity where we have the different processes that are actually going on that students can then sort out themselves and put them into an area. So we call it scaffolding. We need to put things into chunks and break it down. A classic example is carrying out titrations. It's a very complicated process. The first time students meet the burette and the pipette and the big equipment and the calculation. There's all sorts of difficult things that need to go on. But what we can actually do is we can break it down into very, very small chunks and start off with, well, the idea is all we're doing is we're getting a fixed volume of something at one concentration and adding something else. So we can start off with our idea of just having a fixed volume in a measuring cylinder or in a cup or anything, and then adding drops until an indicator goes. And that is a very basic one. And then you could do maybe a microscale one. You could then move on using things like the simulation. The screen experiment that I referred to on the titration is absolutely brilliant, because that lets people drag and drop and put the equipment together and then takes them through the calculation step by step. So for those who find learning difficulty, we have to break it down into small manageable chunks, and also accept that sometimes students won't get to the very high level, and we need to work at them where they are and provide that type of support that they need. So activities where perhaps they're given things and they sort it out themselves, rather than just having that blank sheet of paper.
Thank you, Dorothy, for that response. So chunking and taking it slow as per their needs is basically one approach to deal with this situation, right? Thanks a lot for that. Neeraja?
Yes. Actually, the next question is something related to teacher well-being. And I guess it applies to all teachers across the globe. This question is from Mitali. And the question is, do you feel that the teachers are overworked? I would add my bit to it, and I would like you to share your experiences or your words of wisdom, as we may call it, about what can the teachers do if they feel overworked. How do we get the strength back?
That's a very, very good question. I think teachers do feel overworked at the moment. One of the things that's happening in the UK, and I suspect it's happening around the globe as well, with schools being open, teachers are sometimes having to teach their class, but then half their class might be self-isolating at home, so they're having to put stuff online as well. So it's almost having to do 2 lessons for each class. And sometimes you'll come in and you may not realise what the situation is. So teachers are finding it very, very difficult. And I think they are feeling the pressures in school, with the next lot of exams won't be that far away, and are working very hard, and also feeling out of their comfort zone for having to do things that, let's face it, teachers, in my experience, weren't very good at IT, and doing this sort of thing that we're doing prior 6 months ago, I would never really have talked to a teacher over a webcam very much. So the situation is difficult. And I think the only thing that we can do for teachers in terms of well-being is, first of all, reassure them that pretty much all teachers everywhere are having the same problems and the same issues, and they do have to switch off. And whether that is making a time when they stop work, because you could work all the time and do something else. At the moment in England, we have just started another lockdown period on Thursday. So we're not meant to be going out very much. A lot of the recreation things you would do aren't happening. So it's having to find something that you can actually do, whether it's getting outside, getting some fresh air, getting some exercise, and being able to turn off, I think, is the hardest thing. And I know if I was in the classroom at the moment, I would be finding that very, very difficult as well. So I think in terms of teacher well-being, you have to get to the stage where you think, I've done everything I can, I've prepared it the best I can, now I'm going to stop, do something with my family, have a break, do something else. And it's hard.
You know, I agree with you on that one. And I guess one of the more important thing that we have started doing, and this webinar series came in as a result of that, was to actually share with other teachers and, learn from each other's experiences, especially in the COVID times, what can be done to, help each other out in every possible way. And I'm sure that your experiments today, the microscale experiments, have helped them a lot with a question that they always had as to what to do with the practicals, what to do with the chemistry experiments, especially because most of the supplies or the lab itself was available at school, and school now the students being stuck at home, they don't have that. So thank you for sharing such a wonderful list of microscale experiments. And Jaya ma'am has been also kind to share that on the chat here, so everyone can have a look at the websites and explore themselves about various kinds of experiments that can be done. Of course, some of the material might be very relevant to the UK, but we can always find an alternative material here. So I guess tulips are not readily available in India. So a lot of people were asking what to do if we don't get tulips.
Oh, many plants.
Yeah. So yeah, we can always find Indian flowers that will work for this particular reaction. So the idea is to share with each other and figure out if somebody else has an answer to your question, please, feel free to ask your questions here as well. Thank you, Dorothy, again for such a wonderful webinar. Sorry for the glitch in the, I lost my internet for a minute there, and it collapsed the whole Zoom settings. But thank you for being with us. And I thank everyone in the audience also for being with us today. Let me just share a small teaser for our next webinar. So today is 7th of November, and we do not have a webinar next week as it's Diwali, so we do want you to really enjoy Diwali at home with your family. So we will meet a week after Diwali. So please kindly note the change that we will not be meeting next Saturday, but we will be meeting a Saturday after that. So let me just share my screen. Thank you for watching today's webinar. If you have any particular questions for Dorothy, do write to us. But please join us for the 10th webinar, which is Developing 21st Century Skills, Makerspace in STEM Education, by Professor Rekha Kaul and Professor Rachel Sheffield from Curtin University, Australia. Thank you.